APAB Calculus. We're doing section 8.7, which is actually something we cover in chapter 2. It's L'Hopital's rule. So before we get started on L'Hopital's rule, we should talk about what indeterminate forms are. And I'm going to explain in a drastically oversimplified way what it means to be an indeterminate form. It's certainly not the entire definition. It's just an easy way to kind of reason it out in your head. So samples of indeterminate forms are things like 0 over 0, which we've seen before when we were evaluating limits in 1.3 and we had to simplify algebraically. Infinity over infinity, 0 times infinity, 1 to the infinity, 0 to the 0, and infinity minus infinity. So what makes these things indeterminate forms? So a really sort of slapdash way to think about it is that essentially it creates a paradox between two things that you know to be math facts, but they both can't be true in this scenario. So the easiest one to show you that with is 0 raised to the 0 power. I think most of us are comfortable with the fact that 0 to any power is 0. Like 0 squared should be 0, right? So when I say 0 to a power is 0, what I'm saying is, so if I said, what's 0 squared? You'd say 0. And if I said, what's 0 cubed? You'd say 0. And if I said, what's 0 to the 10th? You'd say, oh, it's 0, right? So 0 to a power should give you 0. But if I say that a number to the 0 power gives you an answer, you should tell me that's 1, right? Like if I said, what's 5 to the 0? You'd say 1. What's 6 to the 0? You'd say 1. What's 507 to the 0 power? You'd say 1. So one of these rules says that if 0 is the base of your exponential expression, you should get a 0 answer. But the other rule says that if 0 is the exponent, you should get a different answer. You should get a 1. And so 0 raised to the 0 can't be both of those two things simultaneously, right? Like all of computer science is built on the fact that 1s and 0s are different. So because it can't be both of those rules simultaneously, it's what we call an indeterminate form. It is neither 0 nor 1. It does not have a numerical value. It is called an indeterminate form. There are other examples of that, right? So if you look at some of these other ones, I think the 1 to the infinity is another classic example, right? If you put 1 to any power, you should get a 1 back, right? 1 squared is 1, 1 cubed is 1, 1 to the 50th is 1. But if you have something raised to an infinitely large power, you should get an infinite answer. So like 2 to the infinity is infinity, 3 to the infinity, infinite, 7 to the infinity, infinite. So the issue here is that when you raise 1 to the infinity, one rule says you should get a 1 out, and the other rule says you should get something infinitely large. You can't have both of those things, so it's indeterminate. The same rule with infinity minus infinity. If you add or subtract, or if you involve infinities in arithmetic, you get an infinite answer, right? But if you subtract something from itself, you should get 0, right? So like 5 minus 5 should give you 0. 10 minus 10 should give you 0. 1 minus 1 should give you 0. So by that logic, infinity minus infinity should give you 0. But if you include infinity in any arithmetic calculations, like adding and subtracting, you get something infinitely large. So here you have a contradiction. Do you get 0 or do you get infinity? Well, you can't get both, so it's an indeterminate form. Same thing with 0 times infinity, right? If you multiply something by 0, you should get a 0. 0 times 5, 0. 0 times 10, 0. 0 times 100, 0. But if you multiply something by infinity, you should get something infinitely large, right? 2 times infinity is infinite. 5 times infinity is infinite. Negative 7 times infinity is still infinite. It's just negative. So the issue here is the answer 0 or is it infinity? Well, it can't be both, so indeterminate form. That's kind of the logic, right? Same idea with with infinity over infinity, right? Something over itself should give you 1, but the second you start involving infinity in these calculations, that's not how it works, right? It should be infinitely large. Same thing with 0 over 0. You're not allowed to mathematically divide by 0, so that shouldn't be able to be an answer at all, but then also something over itself is 1, so again, indeterminate form. Okay, cool. So now that we know what those are, if we look at two specific versions of these indeterminate forms, and the two that we're going to look at here are these guys first, what we're going to end up doing with these is we're going to end up finding a way to rewrite them into these two to do L'Hopital's rule. So the two easiest examples are 0 over 0 or infinity over infinity. Again, pluses or minuses don't matter when we talk about that. It could be a positive infinity over infinity, or it could be negative infinity over an infinity. It doesn't matter. Either way, infinity over infinity is indeterminate. 0 over 0 is indeterminate. So, okay, so L'Hopital's rule. So I always call it just LHOP, which is not great. You'll see me write that in the notes. I mean, it's L'Hopital's. But when you say it, but I usually write LHOP when I write it in my notes. So just so you're aware. So L'Hopital's rule. If the limit as x approaches c of f of x over g of x is one of those two indeterminate forms, 0 over 0 or infinity over infinity, again, plus or minus signs are irrelevant, it could have a positive or negative, we don't care, then you are allowed to do a thing that is not the quotient rule, because you're not differentiating this whole expression. What you're doing is that limit is the same as the limit as x approaches c of f prime of x over g prime of x. Now, what we're going to do as our first example is we're going to do this with a thing that you actually, in theory, already know the answer to. We're going to evaluate the limit as x approaches 0 of sine x over x. Now, I asked you to memorize this way back during limit stuff in maybe like 1.3 or 1.4, that this answer should be a 1. But at the time, I said, hey, you're just going to have to deal with it and memorize it till we get to our second chapter, and here we are, so now we get to walk through it. When I plug in, right, if I try to plug in, I get sine of 0 over 0, which is definitely 0 over 0. That is never the answer, right? That's never the answer. But what it tells me is that I'm okay to do L'Hopital's. So again, I always write it as I'm okay to lop. Okay? So that means that the limit as x approaches 0 of sine x over x is the same as the limit as x approaches 0 of the derivative of sine x, which is cosine x, on top of the derivative of x, which is a 1. Well, now when I plug in, I get cosine 0 over 1, which is 1 over 1. And look, my answer is 1, right? So again, when we learned this section or so back, I said, or a chapter, I guess, back, I said, hey, I'm going to show you how to do that logically at some point, but for now, you just have to take my word for it, okay? So let's go ahead and do a P1 that's the same concept. So inch this guy back here. All right, so for P1, I'm going to have you find the limit as x approaches 0 of 1 minus cosine x over x, which is another one that in theory you memorize, right? So way back when I asked you, again, it was like a chapter ago, in theory you memorized it and you know that the answer is 0, right? So again, in theory you memorize it, you know the answer is 0, but I want you to actually walk through it with L'Hopital's. So pause me if you want to do it by yourself or do it with me. So when I plug in, I get 1 minus cosine of 0, which is a 1, over a 0. So that's 0 over 0. This is never the answer, right? It's never the answer. But what it does tell me is that I'm okay to do L'Hopital's, okay? So I'm going to get that the limit as x approaches 0 of 1 minus cosine x over x is equal to the limit as x approaches 0 of, and I'm going to differentiate the top. I'm going to get a 0. A negative in front of the derivative of cosine would be a negative of a negative sign. So that'll be plus sine x over 1. So now when I plug in, I get 0 plus 0 over 1, which is totally 0, right? So essentially, I'm allowed to use L'Hopital's if when I plug in, I get one of these indeterminate forms, right? And then I use L'Hopital's until I stop getting indeterminate forms. When I stop getting indeterminate forms, I have my answer. So here, when I stopped, it was a 1, and here, when I stopped, it was a 0. So we are going to do a couple examples where we apply L'Hopital's multiple times in a row, because sometimes you have to keep L'Hopitaling in order to get your answer. Cool. So let's do another one. So for our example 2, rather, my bad. Let's do the limit as x approaches 0 of e to the 3x minus 1 over, let's just do it, let's do 2x, okay? And then for a P2, let's do the limit as x approaches 0 of e, let's do 5x over 1 minus e to the 2x. Cool. Sure. Okay. So, I'm going to walk you through E2, and then we can try P2. Okay, so the first thing I'm going to do is I'm going to plug in and see what happens, right? When I plug in, I get 1 minus 1, because e to the 0 would be 1, over a 0. So that's definitely 0 over 0. That's not the answer, but what it tells me is I'm okay to do L'Hopital's, right? So now this is going to be equal to the limit as x approaches 0 of the derivative of e to the stuff. Now this is going to have a chain rule, right? Because my 3x is inside the e, is going to be e to the stuff times the derivative of the stuff, right? And then the derivative of the 1 is 0, so that's fine. And on the bottom, the derivative of 2x is just a 2. So if I clean this up, the 0's gone, and essentially I have that this is the limit, as x approaches 0, of a 3e to the 3x over 2. So now I'm going to go ahead and try and plug in, right? I should try and plug in after each step, even if I'm going to have to do L'Hopital's a bunch of times. But here I'm not going to have to do it a bunch of times, because I'm going to get 3e to the 0 over 2, which is totally a 3 halves. Now you can try P2 by yourself if you want by just pausing me, and otherwise I'm going to go ahead and do it. So again, when I plug in, I get a 0 on top of a 1 minus 1, which is totally 0 over 0, so I'm okay to do L'Hopital's, right? So I'm going to get that this is the limit as x approaches 0 of 5 on top of 0 minus derivative of e to the 2x is e to the 2x times 2, right? It's a chain rule again, right? So I'm going to get that this is the limit as x approaches 0 of a 5 on top of a negative 2e to the 2x. When I plug in, I get 5 over negative 2 times 1, which is totally 5 over negative 2, right? Or a negative 2.5 or whatever you want. So that's kind of the gist of it, right? Let's do one that has an infinity over an infinity. Okay. So we're going to do an infinity over an infinity. Let's do one where we need to do it a couple times. So let's do an E3 that has the limit as x approaches infinity of 3x squared plus 2x minus 1 over a 4x squared minus 6. Okay, now some of you looking at this might be like, wait a second, I can use logic to tell you the answer right now. And if you can, that's dope, and it means I did something right before. But we'll walk through it in a sec. So we'll do this. We approach negative infinity. Let's do a 6x squared minus 5 over... let's do an x cubed plus 3x minus 1. Great. Okay. Cool. Yeah. All right. So again, if you're looking at these and you're like, I can spot the answer right away, then I am happy about that because it means that logically you're able to see what's happening. If you look at this and your brain says, wait a sec, limit as we approach infinity, only the leading coefficients matter. If your brain is able to logic you to the answer that is 3 over 4, then your brain is awesome. Congrats, brain, right? And that's awesome, right? Totally great. If your brain is not there, that's fine. You can also just do L'Hopital's. So here's the issue. When I plug in, right, I'm going to get a bunch of infinite stuff on the top and a bunch of infinite stuff on the bottom, right? That's the shortest answer here, right? When I plug in, I'm going to get infinity plus an infinity minus a 1 over an infinity minus a 6, which is definitely something infinitely big over infinitely big. So I'm okay to L'Hopital's, right? So when I do L'Hopital's, the limit as x approaches infinity, I'm going to differentiate the top, which is going to give me a 6x plus 2, right? Because the 1 differentiates away to 0. And I'm going to get an 8x on the bottom, and the 6 is going to disappear. And then I plug in again, and I'm like, oh, look, that's still an infinity plus 2 over an infinity. Yeah, I'm still okay to L'Hopital's again, right? Because it's still something infinitely big over an infinity. So I differentiate again, and I get a 6 over an 8, which is totally just a 3/4 and is totally the answer that you might have been able to logic your way through. And that's not wrong. That's awesome. Congratulations. If you didn't see that, that's okay. Remember that there's multiple ways to do most problems. There are very few problems where we get boxed into only being able to picture them one way. The more ways that we can picture and quantify problems, the better off we are, because some days your brain's just going to completely go kaput on you and you're not going to know what to do. All right? And that's everybody, right? Okay. Same thing with P3. Pause me if you don't want me to do it. If you can logic your way through to noticing that the degree on the bottom is bigger, and so your logic is telling you that that means the answer is going to end up being a finite number over an infinity, right? If you're able to logic your way to the fact that this is going to end up being a 0 because you're going to get a finite number over an infinity, you're not wrong, and that's great. If you're not able to logic your way to that, that's also okay, right? So when I plug in, I try plugging in, and sure enough, I get a bunch of infinities is the short answer. I get something infinitely big on the top, and I get something infinitely big on the bottom. The top is essentially going to be a positive infinity. The bottom's going to net negative because the infinity cubed is going to be way bigger than the other infinities. This will be a negative infinity. This will also be a negative infinity. But it doesn't matter. Either way, I'm okay to do L'Hopital's, right? So when I differentiate, sorry, computer fell asleep, I'm going to get a 12x on top of a 3x squared plus 3, right? When I plug in, I get a negative infinity on top of a positive infinity, but it doesn't matter. I'm still okay to L'Hopital's, right? So I differentiate again, and I get a 12 on top of a 6x. Well, when I plug in, that's a 12 on top of something infinitely large, which is definitely 0, right? Because we've established before that anytime you plug in a finite number, right, so this is going to be finite, this is going to be infinite. Anytime you have a finite number over an infinite number, your answer is 0. And that's it, okay? So so we're going to stop here. We'll do a couple more examples that we're going to get progressively harder as we go, but I figure I shouldn't make this video go on forever, so we'll stop here for now.